The key hypothesis this work tries to inspect is the feasibility of performing flip turns, a well-known attribute of a bat-like landing maneuver, through the manipulation of inertial dynamics while excluding aerodynamic forces. Bats possess no energy-hungry motors widely used in flying robots for thrust vectoring, yet they are more capable than any of these systems when agility and, of course, energetic efficiency of flight are concerned. Flying vertebrates apply the combination of inertial dynamics and aerodynamics manipulations to showcase extremely agile maneuvers. Unlike rotary and fixed-wing systems, wherein aerodynamic surfaces such as aileron, rudders, propellers, etc., come with the sole purpose of aerodynamic force adjustments, the wings in these creatures possess more sophisticated arrays of specialization.
The mainstream school of thought, inspired by insect flight, has conceptualized the wing as a massless, rigid structure which is nearly planar and translates as a whole or in 2-3 rigid parts through space.
In this view, wings possess no inertial effect or fast that yield two-time-scale dynamics, permit quasi-static external force descriptions, and tractable dynamical system. Unfortunately, these paradigms fail to provide insight into airborne vertebrate locomotion, and an ingredient of a more complete and biologically realistic model is missing. That is the manipulation of inertial dynamics. The manipulation of inertial dynamics is an underappreciated aspect in existing paradigms.
Landing maneuver is the manifestation of strong interconnections between differential inertial forces and external aerodynamic forces in the powered flight of bats. Landing, which flying vertebrates do it in one way or another for a variety of reasons, is an interesting maneuver to take inspiration from for aerial robot designs. Bats do it in a radically different way. After the self-created stalled condition, they manifest an acrobatic heels above head maneuver that involves catapulting the lower body in a similar way that a freestyle swimmer flip turns.
We describe this maneuver with a hybrid dynamical model. If we divide the dynamical behavior of this airborne object into two modes, mode 1 and mode 2. First mode is governed by external aerodynamic forces. Second mode governed by inertial forces. What encourages us to consider such a model directly stems from inspecting high-speed images of the landing maneuver of bats, and that in a time envelope not exceeding about 1/5 of a second before landing completion. The appendages are fully retracted, strongly suggesting that the external aerodynamic forces are less likely to be as important as other forces. This hybrid model will also allow the examination of each mode individually. Fluid structure interactions are hard to model. However, the aerial flip turns are mainly the result of differential inertial forces and are rigorously explainable by mathematical models through available approaches. To describe mode 1, the current schemes can take a number of experimentally validated and successful forms. Therefore, the focus will be the focus of this work will be on mode 2, and that what would be the best strategy to prepare for a landing through the manipulation of differential inertial forces.
The system dynamics and the equations of motion are described in a coordinate-free fashion. That means a dynamical system on SO3 manifold without considering any local coordinate charts. The numerical integrator obtained from the discrete variational principle exhibits excellent geometric conservation properties, well shown in literature, and because of this, it is used here. In these four equations, the discrete time dynamical system can be resolved first by obtaining an answer to the variations on SO3, which involves solving the discrete time algebraic Riccati equation given by equation 1. However, the solution to the AREs are not unique, and for the solution to belong to SO3, the convex constraint given by equation 4 must be satisfied.
The issue of constraint satisfaction in nonlinear systems, including affine and non-affine control systems, and its separation from the issue of closed-loop system design have been addressed very extensively in nonlinear control theory. Almost all of these works do so by including a filter, which is an auxiliary nonlinear device that operates between the reference command and the input to the closed-loop system. A similar approach is adopted here. The platform that we developed and used in our study is called Harpoon. The overall design allows a limited self-sustained sensing, actuation, computation, and communication between this robot and a master computer that is responsible for costly off-board computations. An actuator adjusts the angular velocity of a bob with respect to the body to create differential inertial forces. This bob is designed to precisely capture the desired body to wing inertia ratio.
Harpoon is considered as the landing gear in a morphofunctional machine that is being developed currently at NU. For more information about this robot, please visit our website and YouTube channel. Harpoon platform is laser cut from a thin carbon fiber plate and hosts actuators, power electronics, a receiver, and a processor. A trigger mechanism is unlatched and releases the landing gear once the robot has been reoriented towards the landing surface. Since the projectile is charged with massive elastic energy beyond the output performance of the trigger actuator, a force amplifier with 1:40 mechanical advantage is designed and fabricated at millimeter scale. In our experiments, only the longitudinal motion is considered. The framework was tested in a series of experiments devised with an off-board computer, motion capture system, and high-speed imaging equipment. The computer automated releaser mechanism releases the robot with zero angular momentum in a free fall configuration, while the motion capture system captures the body and appendage orientations. The commanded angular velocities of the bob are resolved off-board and transmitted to the robot for the desired body orientation.
Thank you for your attention. For more information, please visit our website and our YouTube channel.